Okay. We were talking about yesterday. 7-4 we did similar parts of triangles, parallel lines. Yesterday, what were we doing? You had a worksheet. You were doing great on it. I know it had median, altitude, and what was the other thing? Angle bisectors. Okay, and it still was just you set up a proportion, you cross multiply, and nothing's going to change today. Notice one of the key words again, proportional. We're still going to set up a proportion. We're still going to cross multiply. So if you're still making mistakes doing that, you're still going to do awful on this test. If you've not finished your 7173 test, you're in big trouble. I'm typing in the 0 later today. You need to come see me. Okay. A dilation is what we're going to talk about today. Your favorite section so far in my class, the easiest one, was probably the one on reflections, rotations, and translations. We all liked that one. It was easy to see. A dilation is a transformation, so it's in the same neck of the woods as that. The only difference with a dilation is that those were congruence transformations, and these are similar transformations, so they don't have to be the same size. Okay, what part of your body do you get dilated? Okay, and when your eyes get dilated, what happens to your pupil?
They get smaller.
Okay, and then it could also go the other way. It could get really large. So if you have everything gets larger, it's called an enlargement. If everything's getting smaller, it's called a reduction. Okay, what have we been calculating every single section since 7-1? The scale factor. So we're again going to find a scale factor today. The scale factor of a dilation, and I'm not even going to read the rest of it. It's normally what we've been doing where you compare the sides, make sure you get the same number. If it's a reduction, so everything's getting smaller, you're expecting a fraction. If it's an enlargement, so everything's getting bigger, you're expecting a whole number. Not a fraction, a much bigger, not necessarily a whole number, but a number bigger than 1. Okay, so the hardest thing about this is deciding who was there first. So you have to read the directions. It says A to B, so A was first. Was A enlarged to B, or B is a reduction? Tell me the relationship between A and B. It is a reduction, so we're expecting to get a fraction for our scale factor. Okay, some of the scale factors are easy to calculate. For instance, this is silly of me, but I'm going to go on to the second one, which is a rectangle. It says A to B. Is that an enlargement or a reduction? That is an enlargement, so we're expecting to get a whole number. It is easier to calculate the scale factor on B than it is on A. Does anyone know why? Because it's because of the shape, because it's a rectangle. It's easier to count. So to figure out the scale factor, I'm going to count along the bottom. I need to know how many squares. I'm going to count along A's bottom as well. Okay, how long was A? B was 6. And then A was 2. Okay, I always put the original in the bottom, so I'm putting A in the bottom. And I get 3 over 1, which is 3. And I know I'm right because an enlargement was supposed to be a whole number. It was, or at least a number bigger than 1. So I know it was an enlargement. So I have to do the same thing with all the other sides. So if I counted up here, it'd be 6, up 2 again. And if I count on the sides, 1, 2, 3, 1, 1, 2, 3, 1. They all reduce to 3, so my scale factor is 3, and I'm positive that those are similar figures. Does everyone understand how I was counting? Okay, if Trey wants to argue that he doesn't want to count all the sides because he understands a rectangle has the same on the top and bottom and the same on the sides, and he only needs to do this and this, and he uses his words, it's fine. I get that the middle ones were silly. Okay, so we're going to do A the same way. So we can count the bottom of A and the bottom of B. I need to know how long this is. I need to know how long this is. 2? Okay, is it 6 over 3? She said 6 over 3. Is that correct? I agree that it's 3 across here and 6 across here. I'm asking about the fraction itself. Is this an enlargement or a reduction? Is Danny correct? No, because she's going to end up getting a number bigger than 1. Again, I always make sure I put a in the denominator. I put a in the denominator down here because it came first. I'm going to put a in the denominator up here. So it should be 3, which was b, over 6, which is 1/2. Always put whatever you counted from a in the denominator. Okay, someone count the side and tell me what they get for it. And what was the other one? Say it. 2. And this is no glasses. You're still doing it. Awesome. That's 1/2. Perfect. And then here is why example A is harder than example B. How on earth are we going to do the last 2 sides that are tilted? We can't count those. What are we going to do? We are not going to use Pythagorean theorem. How do we figure out how long it is from here to here? We could use the distance formula. So if you're friends with the distance formula, that's a great idea. You can use the distance formula on this piece and the distance formula on this piece and calculate it. There are about 5 in the room who would say the distance formula is their friend. The other 20 or 15 or whatever are like me, and they really wish that Ms. Compton could show them an easier way than that. And I can show you a trick. So Grant has 2 options. He can either, he's going to count up and over regardless. So he went up 1, 2, 3, 4. He went over 1, 2, 3, 4, 5, 6. He'll count it with the other one. He went up 1, 2. He went over 1, 2, 3. I counted that wrong. 1, 2, 3, 4. 1, 2, 3. Is that right? And then he could say, Miss Compton, do you not know 4 divided by 2 is 2, 6 divided by 2 is 3? Like, those two are obviously similar. Clearly, one is a multiple of the other. He could just write that on his test, and that would be okay. I would probably give Grant his points. Would I be more impressed if he did the distance formula? Yes. Or I could show Grant a cheat for the distance formula. So instead of actually doing x2 minus x1 squared and y2 minus y1 squared, he can use the numbers he counted to plug in the formula. So he counted up 4, so 4 squared. He counted over 6, so 6 squared. That's 16 plus 36. That's the square root of 52. He could do the same thing with the other piece. He counted up 2, that's 2 squared. He counted over 3, that's 3 squared. So he's got 4 plus 9, which is 13. Well, that looks insane, but if you type in your calculator, square root of 13 over square root of 52, you'll be surprised at what you get. I'll say it again in a second, Katie. What did you get? Square root of 13 over square root of 52? That is not what I got. Did you put everybody in parentheses? What's checking in meeting? You got to put parentheses on 13. If 13 is parentheses, close it. Oh. And then go around for 15. I thought it was 52. It was 52. You need to change it. Please tell me you got 1/2. Okay, good. Okay, so how did Miss Compton do that voodoo magic? Again, so no one wants to remember the distance formula. I got it. I understand. There's a cheat to the distance formula. Instead of actually doing x2 minus x1 squared, y2 minus y1 squared, instead you can count from point A to point B. So we counted up 4 and over 6. So I plug in 4 squared and 6 squared into the distance formula. 4 squared is 16, 6 squared is 36. That ends up giving me square root of 52. Instead of actually calculating the distance formula, I can count up 2 over 3. So 2 squared, that's 4. 3 squared, that's 9. It ends up giving you square root of 13. This over this ends up being our same old scale factor. We got 1/2 every single time. If you're really trying to show me you can calculate the scale factor for all 3 sides, you would want to do something like that. If you just want to do what I said Grant could do the cheater man's way, where he at least shows me he counted and he understood they were proportional, because 4 divided by 2 is 2, 6 divided by 2 is 3. If he just wants to show me that, that's fine too. But he's got to do something to at least show me that he didn't just skip the third side. Okay, I went way too many details on that one. Are there any questions on A or B? So basically, is it enlargement or reduction? Can you calculate the scale factor? Then we get to example 3. It's the only one that's a little different. So in A and B, we were assuming that everyone was already similar. We just had to prove it. In the third example, we don't even know for sure they're similar. So we're still going to take the same steps.
At this time, can we have who's to the gym for their pictures? Who's. Thank you.
We're still going to take the same steps. This is what happens. They call and they announce. We get distracted. We have to get focused again, then we can talk. It's ridiculous. The whole day is ridiculous. Okay. So if you have one like this that says verify, it's going to be okay if you find out they're not similar. So just know that there's potential for some trick ones. Okay, who came first in this? Is MNO the original? That should be an N. Or is it DFG? Who is the original? Read. It says original MNO. Okay, so is this an enlargement or a reduction? Okay, so we need to get a fraction kind of answer. We can easily count MN. How long is M to N? How long is D to F? I need to know. What did you say? Someone please tell me. Lord, I've already counted. Okay, MN is 12. And then what was DF? 4. Okay, 4 over 12, which reduces to 1/3. Again, if you got 3 over 1, clearly you didn't pay attention that this was a reduction. Okay, I need you to count MO and GD. And I need you to not be a 9th grader. 3 over 9? Thank you. Which is 1/3. And then you can either impress me without the giggle fest. You can either impress me and count and show me like we just did with our top example that ON and GF are also proportional by 1/3. Or you could try to argue something else, because there have been 3 ways we've been arguing for similarity, and they're still on the board. What were the 3 ways we can argue similarity? Okay, so if you want to calculate the third one, you're arguing side, side, side. I would be super impressed with that. Can Nick argue a different one for this example? Look at the triangles given. Can Nick argue a different answer for this example? What can he argue? Because it looks like it's a right angle in both of them, and if Tilly's really trying to impress me, she would prove to me that that is a 90-degree angle, that those 2 lines are perpendicular and those 2 lines are perpendicular. Otherwise, she could just write, it looks like they are the same angles. So this is side angle side, so I'm not going to bother to figure out that third side because I'm tired of doing math today in math class. Are there any questions about this? Okay, that's nice.